Okay, in this chapter, we're going to be looking at the composition of substances and solutions. And the chapter starts off with kind of a review of what we used to do, or what we did in intro, which was figuring out the molecular mass of a molecule. Molecule we have here is CHCl3. And to refresh our memory, we actually just get the symbols breakdown and the number there are, and then get these numbers off the periodic table. Now this other one, I got the digits like what we have on our periodic table from that I provide on the test, and they have more digits, but you will find that you don't need to worry about those. As long as you got 2 decimal places for many things, and you want to get 4 significant figures for hydrogen, helium, and lithium, and beryllium, and so at least 4 significant figures or 2 decimal places, and you should be fine to get that answer. But you just go through the calculations and add them up. If it's a bigger one, you just actually combine more things. Sometimes you might be given a structure, and you'll actually have to go through and count all the atoms and such. And so this is aspirin, acetylsalicylic acid, with 9 carbons, 8 hydrogens, and 4 oxygens, and it shows how to go through that whole same process. And just as a reminder, we're going to practice this with ibuprofen. So we have 13 carbons and 18 hydrogens and 2 oxygens. And from the periodic table, I get 12.01 AMUs for carbon, 1.008 AMUs for hydrogen, and 16.00 for oxygen. And calculator, 13 times 12.01 plus 18 times 1.008 plus 2 times 16, 32. And we get a mass of a molecular mass of 206.27. Units would be AMUs. All right, now technically we do the same thing with ionic compounds, but it's not proper to say molecular mass, because on ionic compounds there's not really a molecule. There's not just a single NaCl around in there anywhere. There is a ratio of 1 sodium for 1 chlorine. So we actually call it a formula mass more properly. Formula mass just says, all right, if it was a molecule, or that is that ratio, what's the mass of that particular ratio? And even with things like aluminum sulfate, the crystal structure gets kind of complex. That's what they're trying to show here. It's supposed to be trying to look like it's in 3 dimensions. But if we wanted to figure out its formula mass, we are just actually getting the aluminum and the sulfate, and we're going to figure out what the relationship is, just the same way we did it for our last chapter. So that's a positive 3 and minus 2. So aluminum sulfate has the formula of Al2SO4 3. And so there'd be 2 aluminums, 1 sulfur times 3, 3 sulfurs, 4 oxygens times 3, 12 oxygens. And you just go through the same process to get that molecular weight in AMUs. Okay, on accounting are atoms. Now, in everything, when you get a group of things, you count by a group, like a dozen donuts, things like that. Well, in the chemistry world, we need to do something a lot larger than a dozen, simply because there are atoms are very, 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 very small, and we never deal with them directly. So ages ago, a bunch of the guys, the chemists, got together and said, all right, carbon 12 has 6 protons and 6 neutrons. Because of that 12, let's say it weighs 12 AMUs. That's easy enough. And someone else said, all right, how many of these, so take these individual atoms, individuals, I'll just do that, and let's see, how many do I need times what would take and give us a mass of 12 grams. So 12 AMUs is the mass of 1 atom. And then they want to know how many atoms would it take to get a mass of 12 grams. Biggest reason they did that is to give us the ability to say that grams per mole is roughly the same as AMUs for everything. It just turns out that it's a really large number, and it is the Avogadro's number, 6.022 times 10 to the 23rd atoms. It's true for any substance. If you have that many atoms, the mass of the atom in AMUs would be the exact same as the mass of in grams for that entire mole worth of those atoms. So each one of these numbers listed on this in the picture is the molecular weight of each of these individual atoms. And that does mean that each one of these samples, that is 1 mole of each of those atoms. Every single one of those pictures has each one of those subsections has 6.022 times 10 to the 23rd atoms. All right, because math works the way it is, it doesn't matter if it's a pure substance or a molecule. So we have a few things that we have a mole's worth of them. Now, this yellow, it's just typically called sulfur, but it turns out sulfur is never really found by itself. It's always found as S8. The red powder is mercury iodide. And then our other two pictures, we have octanol. And then our other picture is methanol. But each of those contains 1 mole worth of atoms, and they've got that by just weighing it out. The weight here is the molecular weight of octanol. The weight here is the molecular weight of mercury iodide. And that's what they did. They actually flat out weighed it out and determined the mass. Okay, to convert these and to actually use it, we actually can use those molecular weights as conversion factors. So if I wanted to say, for instance, how many moles of potassium are in 15 grams, I take my 15 grams, and what I'm going to use here is the molecular weight, or the molar mass, of potassium to then convert grams into moles. And it turns out 1 mole of potassium, I just get my periodic table out, and it happens to weigh 39.10 grams is the molar mass of a single atom of potassium. So to do this conversion, we just take 15 and we divide it by 39.1, and we get that that is 0.384 moles of potassium. Now, if we want to take it a step further and get the atoms, we'll have to use Avogadro's number. Now, we can't go from grams directly to atoms. We'll always have to actually convert to moles first. So this conversion looks slightly different. So we have that mass of copper. We're still going to use the molecular weight of copper to convert the grams into moles. And copper's molecular weight is 63.55 grams. And that mole gets turned into atoms using Avogadro's number. Now, this is something that my calculator might actually do this math slightly different than yours. So do practice, make sure yours works the same, or that you get the same answer. So 15 divided by 63.55 times 6.022. And I'm going to use this EE button. Oh, I didn't get my other 2 in there. That EE button says times 10, and then I just put in 23. And I get that that 15 grams is 1.42 times 10 to the 23rd atoms. All right, and we're going to do another one of these. Got glycine here, which is an amino acid. It's one of our basic building blocks of all proteins. So if you ate this morning, you probably got some glycine in your diet. All right, so we want to figure out how many moles of glycine are in 28.35. Got a couple things we have to do here. We know we want to do that conversion of grams to moles, and we need the molecular weight there. So we need to actually figure out the molecular weight of our glycine. So we have 2 carbons, and we have 5 hydrogens, and we have 2 oxygens and 1 nitrogen. That's 12.01 and 1.008 and 16 and 14.01. So 2 times 12.01 plus 5 times 1.008 plus 32 plus 14.01. Molecular weight of glycine is, oh, I made it go away before I read it, 75.07 grams. And that's all we'll need to do. So we take that 28.35 divided by my previous answer, and I get a molecule. I get that we have 0.3776 moles of glycine there. All right, how about this? We're gonna like this molecule up above here is saccharin, and we want to know how many molecules of saccharin are present in 40 milligrams. All right, a lot more to do on this one because I give you the 40, and I'm going to actually immediately turn that into grams. And I know I need to turn grams into moles. I didn't give you the molecular weight. I didn't even give you the molecular formula. So we have to figure out the molecular formula. So I got carbons, 1, 2, 3, 4, 5, 6, 7 carbons. I have hydrogens, 1, 2, 3, 4, 5 hydrogens. I have oxygens, 1, 2, 3. I have sulfur, and I have a nitrogen. So 7 carbons, 5 hydrogens, 3 oxygens, 1 sulfur, and 1 nitrogen. All right, let's get the molecular weight of that. So 7 times 12.01 and 5 times 1.008 plus 3 times 16 plus 32.06 plus 14.01, I get a molar mass of 183.18. But I don't want to know the I don't want to know the moles. I want the actual individual molecules. So I need to actually add in here that 1 mole is 6.022 times 10 to the 23rd molecules. So take 0.04 divided by that molecular weight we just calculated, and then multiply that by 6.022 times 10 to the 23rd. And we get 1.31 10 to the 20th. All right. The next one follows that calculation up by asking how many carbon atoms are present. Well, if we had been asked that directly, we really would do this everything exactly the same as we did up here. So we would be converting our grams into moles, which is almost always the first step when you get grams of a substance. But 1 molecule isn't what we want. We want to know how many carbon atoms are in that molecule. So we're just going to say this. Well, for every one of the saccharins, there are 7 carbons. So technically, all we need to do is take the number we just calculated, because the first part of the equation is exactly the same. We're just going to multiply that by 7. And that represents the number of carbon atoms in that 40 milligrams. Okay, on to a little bit more complex thing. We're going to calculate an empirical formula of a substance. Now what we have here is the strategy, but this is the strategy they would apply if we just had 2 atoms present. So if it's just like carbon and hydrogen or oxygen and boron, it just need to be 2 atoms. If there's 3, we're just going to add another yellow box and a red box, and we'll add 1 for each one. So we could be almost any number of things. All right, your very first thing you're going to do, typically empirical formula, we actually start with the mass of the atoms present. And what you would do is convert those into moles. Now you do that because we really can't compare mass of an atom to mass of another atom. But moles, especially if they came from the same molecule, will be actually comparable because they will be whole number ratios of each other. Now once you have the moles, you just take whichever one of these 2 is smallest and divide by the smallest. And that should give you a nice whole number ratio. Now there are times you get like 1.5 and 1.33. And outside this class, you get even more fractions. Well, fractions, you will just actually double or triple the number. Because if you double to 1.5, so if it's like a 1 to 1.5, that's really a 2 to 3 ratio. And 1 to 1.3, that's really a 3 to 4 ratio. So we're just actually going to have to get rid of those. And we're going to see that in a couple sample problems so you can see what's going to happen. But that's how we go about getting an empirical formula. All right, we're going to see that with this sample right here. I have something that has carbon, hydrogen, and nitrogen in it, and we want to get the empirical formula. And the first thing we're going to do, see how it gives me a mass of 12.04? We want to just make sure all 3 of these numbers add up to 12.04, because that would actually confirm that it is just carbon, hydrogens, and nitrogens. So 7.34 plus 1.85 plus 2.85 gives us 12.04. So that does tell us that carbon, hydrogen, and nitrogen are the only atoms present. All right, so what we're going to do is we're going to write down all those masses of those individual atoms. And our very first calculation we're going to do is convert those into moles with their molecular weights. And sometimes when you do this, you almost immediately see the ratio, because you might see the same number multiple times. So 7.34 divided by 12.01 gives us 0.611. .85 divided by 1, but it's 1.008. It's going to give me 1.84. I should be writing units down here. And our last one, 2.85 divided by 14.01 is 0.203. All right, now what we're going to do, since the 203 is the smallest, we're going to divide the other 2 by 2.203. So 0.611 divided by 0.203 might not be perfectly an exact whole number, but that's roughly 3. Obviously, If we divide this by itself, that'd just be 1. And the last thing we need to do is take that 1.84 and divide it by 0.203. And we get 9. All right, those whole number ratios are the empirical formula. So this particular compound has an empirical formula of C3H9N. Now, the empirical formula might not be the actual molecular formula. Empirical formula is just that smallest whole number ratio. The actual molecule could have double of each of those. It could be C6H18N2. We'll need to do something more to see what the actual molecular formula is. All right, let's do another one of these. We got nicotine, but this time I gave you percent composition. And we're going to use the percent compositions to turn those into masses. All right, so it's 74% carbon, and it's 8.710% hydrogen, and 17.27% nitrogen. Well, previous slide, we used these with grams. We're kind of going to do the same thing. We're just going to assume we have 100 grams, so each of these are just grams. And then our same first step applies. Let's see what we get here. 74.02 divided by 12.01 is 6.16. Well, 6.163. And 8.710 divided by 1.008 is 8.641. And our last one, 17.27 divided by 14.01 is 1.233. All right, the moles of nitrogen is our smallest, so we're going to divide everything by the 1.233. So that is just 1. That divided by that is 7. And the 6.1 divided by the 1.23 is 5. So we have an empirical formula of C5H7N. All right, now knowing that, can we use this information to get the molecular formula? Well, we can. So our empirical formula, C5H7N, could be the molecular formula, but we know it's at least a multiple of this. So what we actually do to figure this out is we figure out how much this thing would actually weigh, figure out its molecular weight. We don't have to be super precise here, we just need to be close. So I know there are 5 carbons, and carbon weighs 12 AMUs. There are 7 hydrogens that weigh 1, and there's 1 nitrogen that weighs 14. Now, beauty of doing it this way, 5 times 12 is 60. That would bring it up to 74. And this would add another 7 to that. So about 81. All right, but I need to know how much the actual molecule weighs. Does it weigh 81 AMUs? Well, we need the molecular weight. And technically, I give you enough of this. So if we know that 40.57 grams of nicotine is 0.25 moles, we have a ratio between the grams to the moles. Well, ratio between grams to moles, that is the molecular weight. So the molecular weight of nicotine is actually 40.57 divided by 0.25. 162.2. And if I take that 81 I just found, I see that that's half of it. So this empirical formula is half the molecular formula. So the molecular formula must be C10H14N2. So follow that up with, figure out the mass of the empirical formula and compare that to the molecular mass. If they're the same, the empirical formula is the molecular formula. All right. What we've been doing here is figuring out the empirical formula from data we have obtained from something called the combustion train, or something like this. Now, the whole idea here is you take a sample of something and you burn it inside this first chamber. You feed it in a bunch more oxygen and you burn it. Well, if this container is made of something that just is containing carbons and hydrogens and maybe oxygens, it's going to turn into water and carbon dioxide. That's your main products when you do combustion. So we feed in a lot more oxygen and make this reaction go forward. Now, all the hydrogen would get turned into water. So if you weighed this chamber before and after, you'd know exactly how much water was being produced. And same, the carbon gets turned into carbon dioxide. So you weigh this container and weigh the exact carbon dioxide. Well, having the weight of the water and the weight of the carbon dioxide technically tells you the weight of all the hydrogen and all the carbon. Now, we can't do the same thing to get the oxygens. Even though there's oxygen in both these, the oxygen didn't come just from the molecule because we were feeding in oxygen. And if we weren't monitoring how much was going in there, when there's no feasible way that we could, we're not going to know exactly how much oxygen was added. But what we could do, if we had weighed this sample beforehand and we knew that it was only made out of carbons, hydrogens, and oxygens, if we know how much the carbon weighs and know how much the hydrogen weighs, we can solve the oxygen. All right, so we're going to give this a practice on something a little bit more realistic, and a lot more detailed. All right, so we got vitamin C here. It's made out of carbons, hydrogens, oxygens, and we combusted it in that combustion train. And we have a mass of CO2 and we have a mass of water. And we have an original mass. We're going to use all of this to figure out the molecular formula of vitamin C. All right, we're going to start by getting the mass of the CO2 produced and the mass of the water. And all I'm going to do to get those is subtract those numbers. So 85.351 minus 83.050. I'll have 3 decimal places, so that is 2.301. Excuse me. All right, so doing the same thing with the water. So I got 37.961 minus 37.333, which is 0.628 grams of water. All right, now this next thing seems weird, but technically think about it. To get the empirical formula, we needed the mass of carbon, hydrogen, and oxygen. So our first step is to get those masses. All right, we're going to get the mass of the carbon from that CO2. And how we're going to do that was we're going to look at what CO2 is made out of. CO2, carbons and oxygens, has a molecular weight of, we'll just do this right in the calculator, 12.01 plus 32, which is the 2 oxygens, 16 and 16. We get a molecular weight of 44.01. Well, I'm not going to do grams per moles. I know that's how much a CO2 weighs. I really just want the carbon in it. And in CO2, there is 1 carbon. That weighs 12.01 grams. This is almost like a mass percent of the CO2. That's actually what it is. We just using it as a conversion factor. So times 12.01 divided by 44.01, we have that this is a mere 0.6279 grams. All right, we're going to do something similar with that water, 0.628 grams of water. The molecular weight of water is 18.016, one oxygen, two hydrogens, and there are two hydrogens in a water molecule. So 0.628 times 2 times 1.008 divided by 18.016 gives us a mass, this will only be three significant figures, of 0.0703. All right, those two masses came out of this original sample, and everything else in that sample was oxygen. So we're going to do some subtraction of that to figure out what's our mass of oxygen. So 1.535, the entire sample. Subtract out the carbon, and subtract out the hydrogen. And we get that the oxygen is 0.08368. And now that we have those masses of the individual components, we convert them into moles. So the 8368 is in my calculator, so I'm going to start with that, divide by 16, and I get that that is 0.0523 moles of oxygen. And take that 703 that I got up here, divide that by 1.008, and I get that that is 0.0697. And the 0.6279 divided by 12.01 is 0.05228. All right. Technically, those are roughly the same number, right? So this is a 1 and a 1. But what's the hydrogen? What do we get if we take 0.0697 and divide it by that 0.0525? It's not a whole number. It's 1.333, and it's three threes. Well, if we were doing back in math and thinking about it, that's 1 1/3. That actually tells us that we should multiply each one of these numbers by 3. Our empirical formula is C3H4O3. All right, that's not necessarily a molecular formula. Could be. We got to figure out how much it weighs. So I'll do this in the calculator rather than actually doing it quickly. So we have the 3 carbons plus 4 hydrogens plus 3 oxygens gives us an empirical mass of 88.06 and the molecular weight of 176.12 divided by the empirical formula tells us Nice little ratio of 2, which does mean that the molecular formula must be C6H8O6. All right, enough of those empirical formula problems for a bit. We're going to introduce the whole concept of solutions. Now, at first, we're going to be limited in the type of ways we calculate the solutions. Like in a lab setting, most chemistry lab, we flat out use the molarity. Now, to get a concept of what molarity is, we're actually looking at these two samples. You notice that's got that blue color to it. That blue color is coming from a substance called copper nitrate. You notice on this picture, this one's darker than this one. Well, technically, all they did was they actually had this one twice, and they added water to it. They did a dilution. And if you notice, the water is roughly double it. All right, so technically inside the container was the exact same amount of copper nitrate at first. Same mass and the same moles. Well, molarity is a calculation that has the moles in it as a relationship to the volume of the solution it is. It actually does get expanded up to moles over liters. So in a situation like this, you know how it says the same mass, you would have weighed it, and then you would have actually flat out measured that volume, and you would have been able to turn that into a single value that said the concentration. Now we're going to see that on something like this. This is a great example of how we prepare a solution of KMnO4. I should redo this picture because it turns out KMnO4 is a purple color solution. If we'd done on a white background, you would have seen that. You can kind of see it in the bubbles. It's got a very beautiful purple color to it. It's kind of oxidative, so it gets on you. It actually stains you purple for a bit, and then you end up with little black specks. They'll eventually go away, but it oxidizes the skin. All right, but we're going to make a solution of KMnO4 by mixing 4.74 grams of KMnO4 in that flask. Now, this particular flask is something that we call a volumetric flask. These are made this way because that long handle is something to hold on to, and you can swirl these things pretty aggressively. So what you do is you put that sample in there. You'd only fill this flask halfway up with water, and then you can swirl it by hand. The other advantage, sometimes when you make solutions, you actually get what we call exothermic reactions or endothermic reactions, so a big heat change. They either get really hot or really cold. Well, if it's really hot, you don't want to be touching this. Well, glass is such a poor conductor of heat, you can hold on to the top and it won't get hot. The bottom will stay hot, and you can swirl it and you can stay away from it. And then once you get everything dissolved, you just fill it the rest of the way up with water. And on all these, and you can't see it on either one of these pictures, at the very top of any volumetric flask is just a single line. It's not a multiple of lines, it's a single line. And if that line has been on there properly and properly calibrated, you see how this says 1,000 on the side? You might not be able to see it, but it does say 1,000 milliliters, and it does just say it with like that. Well, if it's a properly calibrated volumetric flask, it actually calibrated to be 1,000 with 2 decimal points milliliters, at least in most cases. Almost all the ones we have in the chemistry lab at our school are that accurate. We do have others that aren't, but the ones that the students get to use are pretty darn accurate. All right, so let's figure out what this concentration would be. So we would take that 4.74 grams of KMnO4, and we need to turn it into moles because concentration that we're dealing with is molarity. So I need the molecular weight of KMnO4. I'm going to put that over here. So there's 1 potassium. Potassium has a weight of 39.10. There is 1 manganese, and manganese has a molecular weight of 54.94. And there are 4 oxygens and a molecular weight of 16.00. So our molecular weight of KMnO4 4 times 16 plus 54.94 plus 39.10 is 158.04. All right. If we did that calculation, that would give us the moles of KMnO4. To turn it into a concentration, we take those moles and divide it by the volume in liters, which would be 1.00000 liters. Basically, we're going to get 3 significant figures from the mass, is how that translates. So 4.74 divided by our molecular weight, and then roughly divided by 1. This has a molarity of 0.0300. Molarity is labeled with a capital M. If I'm going to label the container when I'm all done, I would actually label it as 0.030 KMnO4. Put that on a little label. Right, initial it, and then put a date on it, so we know if it does go bad or expires or anything like that. All right, to use these, we can do some very interesting things. Now, I'm going to show you something that shows all the steps similar to what we did, so with conversion factors, and then I'll show you a formula you can use anytime you see the word dilution. All right, so if you read this, we have a solution of, it's a concentrated solution, concentrated at 2.04 molar, and we're going to take 25 milliliters of it and dilute it to 500 milliliters. So we're going to take 25 milliliters of this solution of methanol, that's what that CH3OH is, and we're going to add a bunch of water to it. All right, so to see what this means, or how this happens, we're going to take that 25.0 milliliters. Actually, you know what? Since molarity is moles per liter, I'm going to start right off the bat by changing that 25 milliliters into 0.205 liters. And molarity can always be turned into 2.04 moles per liter. That gives us a conversion factor. That's actually why we end up using concentration so much in chemistry labs, because you can get volumes relatively easy, and we can go right from a volume into moles. And moles is how we count things in chemistry. All right, so this will give us our moles. What we're going to do with those moles is we're going to dilute it to 500 milliliters. So that's our moles in the original solution and the final solution. And this would be the volume of the new solution. I do want that in liters, so I'm going to put that decimal over and move it around. Now watch out how that's worded. Had it said we were adding 500 milliliters, then this would be 525. But it does say it's diluting it to. So we're taking that 25 milliliters and moving the volume up to 500. The total volume is 500. All right, so 0.25 times 2.04 gives us the moles. Divide that by 0.5. Now we have a new concentration. Oh, I was going to say that's not right, but I put in 0.25. How about I do 0.025 times 2.04 and then divide that by 0.5. That's better. 0.102 molal is the new answer. Well, it turns out you don't necessarily need to do all this. I don't even need to convert those volumes. Turns out whenever using dilution, you see that, you can use this equation C1V1 equals C2V2. Concentration times volume equals concentration times volume. And we could have got the same answer by taking concentration, 2.04, times volume, 25.0 milliliters, equals concentration, what we're going to solve for, times volume, 500 milliliters. As long as the concentrations and units are the same and the volume units are the same, this will work. So I don't have to convert the units this way. And technically, we're doing the exact same calculation. 2.04 times 25 divided by 500. Still gives us the 0.102. But dilutions can be quicker if you remember that C1V1 equation. Okay, can't do that so much here. We're not diluting it. We want to know how are we going to prepare a sample. Oh, wait, we are diluting it now if you think about it, aren't you? You want to make 5 liters of a 0.1 molar solution starting with 1.5. Well, if you start with the 1.5 and dilute it, that fits into this category. So C1V1 equals C2V2 should work here. So our concentration that we want is 0.100, and we want 5 liters of it. And we're starting with 1.59 molar. We just need to figure out how much of that original stuff we need to get. So 0.1 times 5 times 5, and then divide it by 1.59. This tells us that we want to get, to make 5 liters, we want 314 milliliters of that stock solution. So you take that 314 milliliters, put it in a container, fill that volume up to 5 liters, and you'd have that 0.1 molar solution. All right. Where molarity is used in the chemistry lab, it's not used in the real world. Real world likes percents. What we have here is a picture of bleach and disinfecting bleach. We'll list somewhere on there that concentration of sodium hypochlorite, which is NOCl. Turns out bleach used for clothes may or may not have sodium hypochlorite anymore. Turns out sodium hypochlorite does damage fabrics. Since the goal of bleach for your clothes is to make things white, they put other whiteners in there that aren't as damaging. So there might not be any extra sodium hypochlorite in some bleaches. But it has to be on there, and that 7.4% is typical. Now, percent-wise, this is a solution, right? So that could be 7.4% of the volume of solution. Well, there's many ways to calculate percents. The various different government controlling agencies decided that that needs to be grams. So what that means is in 100 grams of that solution of the entire bleach container, there is 7.4 grams of straight sodium hypochlorite by mass. That was kind of done and legally changed based on toothpaste fluoride concentrations. Turns out some toothpaste manufacturers were exaggerating the amount of fluoride in their toothpaste by measuring it under their percentages under different techniques. So some legal eagles got it changed. So all percents must be mass unless they're otherwise stated. And you will see that very few places, but you might see a percent and then after it, it says VV. That means it's volume and volume. They are allowed to use those percent numbers, but they have to specify VV if it's volume and volume, MV if it's mass and volume. If it doesn't say anything at all, it must be mass and mass. All right, so rubbing alcohol. Most rubbing alcohols we can buy at the store, 70% volume. We're going to figure out how much, what that means for the actual active ingredient or the actual isopropyl alcohol in there. So if it's 70% isopropyl alcohol, it must mean that the rest is water. So let's figure out how much isopropyl alcohol is actually in a sample. All right, so I have a 355 milliliter bottle. Problem with that volume is to get a mass percent, we need the mass. So our very first step is to convert it into grams using the density of the alcohol. Now, that would be the mass of the entire solution, so the alcohol and the water in there. To turn this mass into just the rubbing alcohol percent, we would actually use this as a conversion factor. For every 100 grams of the solution, there is 70 grams of isopropyl alcohol. And then our math ends up looking something like this. 355 times 0.785 times 0.7. So in that 355 milliliter bottle, about 195 grams is isopropyl alcohol. Okay, other ones that we need to say. We talked about the mass volume percent. The other ones that we see sometimes, parts per million, parts per billion, this really is when the masses are super, 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 super small. This pops up with water. So Michigan right now, still in Flint, Michigan, the lead is something they're having to deal with. It's in controllable numbers, but for a while it wasn't. But the amount that actually makes it dangerous was only 15 parts per billion. All right, what that actually translates to, a part per billion, you actually would take, in this case, we have the mass of the lead compared to that 100 grams of water. And this number was so small, to get this up to 15, they actually ended up multiplying this fraction by 10 to the billionth to get 15 parts per billion. And that is actually that conversion factor. All right, so it is just the same type of mass percent we just did. So what we're going to do is I'm going to change this slide here real quick. We're not going to do this with 300 milliliters of water. We're going to measure out the weight of that water. All right, so if we're working backwards here, we know that 15 parts per billion, we're essentially solving for this if this is 300. That seems weird, right? But we can actually kind of work backwards on this. So if I start with that 15 and then divide by a billion, because that was on, and then I will actually move this over here. So multiply that by, and I'm not going to do 100, I'm going to multiply it by the amount of water we actually had, 300. That number there is all the mass of lead that's in that water, 4.5 times 10 to the negative 6th grams. Now it did ask for micrograms, so to turn this into micrograms, we're going to multiply that by 1 times 10 to the 6th, because there's a million micrograms in a gram. So, I don't need that. I see that that is 4.5 micrograms. That's all that's in those 300 grams of water. Now, the biggest reason it's dangerous is because it builds up in your brain, and if your brain is developing, it slows the development of the brain. So it's very bad and deadly to young children, or at least slows down their development. And that finishes us up with this chapter.